Welcome back 3U and 4C chemistry students. So in our last lesson, we introduced the idea of stoichiometry, which is a process that allows you to calculate quantities of different substances involved in a reaction. So you could figure out things about products or reactants, basically like solving for missing values in a recipe. So we did a very simple example where you were given moles of something in the reaction and then asked to figure out moles of a different substance from that reaction. And that's as far as we went. So today we're going to finish our note on the back and look at some more realistic examples of, what you would actually be solving for. So at the top here, I have kind of the start of a diagram, which I'm going to be adding to as we go through. And then I also have a list of steps that are kind of what you want to follow in your mind whenever you're solving a stoichiometry problem. And a couple of the steps we did the other day when we did some introductory examples. So I'm not going to read through the steps right now. We're just going to start doing an example, and then we'll kind of be jumping around, adding to our diagram and referring to the steps. So the example we're going to do down here asks for what mass of rust, which is iron oxide, would you produce if you had 745 gram piece of iron and then it was on to completely turn into rust. We want to know how much rust we would end up with. And here's the reaction. Iron plus oxygen makes iron oxide. So the first step always in a stoichiometry problem, if you're doing, a textbook question and writing it out, is you should write the balance kind of across the entire page as best you can so that you have lots of room to work. So, on a worksheet, I have done that step for you. So that is number one, write and balance the chemical equation across the entire page. I also have it balanced here for you, but always check to make sure that it's balanced. All right, so step 2 says list all given quantities and required quantities. So required are what you're asked for. Usually we put a question mark and put it under the appropriate column, which I did mention that on our last lesson, that think of each of the substances as a place to organize the information. So if I'm reading what mass of rust, so if I go over here to rust, I'm going to put a question mark, or actually let's do that a little bit different. Instead of question mark, I'm going to say mass equals question mark. Okay, so this is step 2, where I am writing right under the appropriate place what stuff I want or am given. So the other thing is 745 grams of iron metal. So here's iron. So that is something I was given. 745 grams. All right, so that's number 2. Now, because a balanced equation is really saying 4 moles of iron plus 3 moles of oxygen are going to make 2 moles of iron oxide, everything is in moles in a balanced equation. So we are going to have to get this stuff turned into moles. And of course, to do that, we're going to do step 3, calculate the molar masses of any substances that involve a mass. If you don't have mass in some capacity written below the column, you don't need to take your time to do the molar mass. So here we do have 2 masses that we're going to need, but oxygen, I don't need to take time to figure that molar mass out because I'm not doing anything with it in this particular question. So for step 3, we're just going to do our regular old molar masses. Now, a common mistake students make is they get confused by the coefficient 4 and they think the molar mass now has to be multiplied by 4. But if you think about it, it's still molar mass, which says the mass of 1 mole of a substance. So guess what? You're still going to go on your periodic table and look up iron and see that it is 55.85 grams per mole. And that's what you want. It's per mole, not for 4 moles. We'll deal with that 4 later. So that is iron. And then we're going to come over here and we need to know iron oxide. So that is going to be 2 times 55.85 plus 3 times 16, and I believe we get 159.70 grams per mole. Remember, we always keep our 2 decimal places using our Nelson periodic table because you're adding values with 2 decimal places. Okay, that's number 3. Now, convert any given quantity, if it's not in moles already, like last lesson was in moles, so we got to skip this. But if it's not, we need to get it into moles. So that, step 4, is actually the first thing I've kind of shown on this diagram up here. If you are given a mass of something, you totally must turn it into moles of that substance. So in order to do that, you are going to multiply by the molar mass, and of course you're going to set it up with grams on the bottom because you are trying to get rid of grams. So I'm putting question mark grams because this is just a, this is A. I have no idea what A weighs. Okay, so we're going to now do that step for our question, which is step 4. And it's of the given. So the given quantity, so that is here. So we have 745 grams of iron, and we're going to multiply by 55.85 grams on the bottom, 1 mole of iron on top, which gives us, I'm going to just jot down 13.34, but I think I've mentioned in the past, it's really best if you don't clear your calculator. That's how you're going to get the most accurate answer in the end. So we're going to want 3 sig digs in our final answer at some point. Okay. So we've got 1, 2, 3. We've now done number 4. Now, the magical thing about stoichiometry is these coefficients give you this thing called a mole ratio that lets you literally hop from one substance to an entire different substance. So of course we want to hop from iron over to iron oxide, and there's a relationship of 4 iron to 2 iron oxide. That is the mole ratio. So number 5 says use the mole ratio to convert moles of given to moles of required. So let's add that to our diagram. So we're here, we're trying to get from moles of A to moles of B. So this is our new conversion factor that you absolutely have to use in stoichiometry. And if you don't, you haven't done stoichiometry. So because you're starting with A, you're going to have some number of moles of A on the bottom, and you're going to have some number of moles of B on top, is what you would multiply by. So moving down, we will do that. So I want to get rid, oh, I should have actually slashed out those grams there too. We want to get rid of moles of iron. So we look up here, oh, it's 4 moles of iron. And we would like to turn it into moles of iron oxide. Fe2O3, which the coefficient is 2. So it's a 2 to 4 mole ratio. That could be simplified to, 1/2, but it doesn't matter. As long as in your calculator you take your number that you have in there, multiply by 2, divide by 4. Okay, so this is step 5 that we're doing here, and this is our new mole ratio. So new conversion factor, mole ratio. Okay, so 13.4 times 2 divided by 4 is going to give us 6.67 moles. Notice moles of iron are going to cancel, and now we have moles of iron oxide. Okay, So we're getting there. Now, when you take a look at your question, you set it up so you would not forget what your goal was. And you were to solve for mass of iron oxide. So step 6 says convert moles of your required, which we now have, to whatever the question is asking for. It might be mass, where you're going to use molar mass. It might even ask for molecules or particles like atoms or molecules, depending what your substance is. So in that case, you'd use your old Avogadro number conversion factor. So let's just finish up the picture up here and add these. So in our question, we are going from moles of B to a mass of B. So once again, we're going to use molar mass, but this time we're going to have 1 mole of B on the bottom multiplied by some number of grams, whatever that might be. But as I mentioned, the question may have asked you to turn your final answer into pieces or particles, and that is fine as well. So in that case, you would be doing 1 mole of B on the bottom, and Avogadro's number, 6.02 times 10 to the 23 pieces, which might be molecules, depending what it is. Okay, and then just while we're at it, our question started with a mass, but there's no reason our question couldn't have started with, oh, you have so many molecules of substance A, and then ask you about something else. So had that been the case, you would again try to get to moles, and to do that, you would have had 1 mole of A, and then you'd have your particles on the bottom. So 6.02 times 10 to the 23. I'm going to put molecules again, but again, doesn't matter, of A. So molar mass, we've done before. So there's the 2 places you can use it. Avogadro's number, done it before. This is your new one that lets you hop from one substance to another. Okay, so back where we were at step 5, and now 6 says convert to whatever you're asked for. So at this point, I'm going to put 1 mole of iron oxide on the bottom, and then I'm going to remember that I've already calculated the molar mass, and it is 159.7. Moles is going to cancel. This is step 6 that we are now doing, and I get 1,065 grams of iron oxide, which is the right answer. However, based on our given information, we're only allowed 3 significant digits. So I'm going to be forced to do scientific notation, where I'm going to want the 1, the 0, maybe the 6, but I look at the 5 and I know that's going to go up. Scientific notation is always a number between 1 and 9.9, so I'm going to put 1 decimal and then 0.7, and then realize that my decimal got moved from here to here, so that is 3 places, so it's times 10 to the 3 because I have a very small number and I need to remind people that it is actually a big number. So 1.07 times 10 to the 3 grams of iron oxide is our final answer. And of course, because it is times 10 to the 3 grams, 1,000 grams is actually a kilogram. So your answer could also be 1.07 kilograms. That would be perfectly acceptable as well. Okay, so that is it for today. Just remember, you don't have to start with mass and end with mass. You could start with particles and with mass. You could start with particles and with particles. You can do any combination. So hopefully that little diagram will help you keep organized. Okay, until next time, we'll see you later.